Thank you. Thank you. Hi, everyone. My name is Ningyu and from Peking University. And today I want to talk about a project that we've done with Ember Group, a well-known blockchain security company. And our work is about fuzzing the latest NTFS of file system in Linux kernel. So let's begin. Talking about a file system, we all know that it is a key component in our computer and many components can interact with it. Whereas operating systems plays a most important role. It can organize files and directories in file system. Typically, an operating system has its specific file system like an ext4 for Linux and APFS for Mac. Moreover, except for operating systems and ordinary users can also interact with the underlying file system. It can be done by two factors, the image and the file operations. Specifically, users can mount an image, the disk, on an operating system or perform some file operations like fread and fwrite. Intuitively, they can be two security factors that impact the underlying file systems. So let's talk about NTFS. NTFS stands for New Technology File System, and it is a proprietary journaling file system developed by Microsoft, which means that its implementation is not open source at all. Moreover, it is the default file system of the Windows NT family starting NT 3.1. It's around 1990s. So lots of disks are organized by such file system. To read and write this disk for users of Linux kernel, it starts to merge NTFS 3 and NTFS implementation into its upstream. All such things have been done in late 2021. And as security researchers, we all know that a new system is always a good target for security research because there may be lots of bugs and vulnerabilities. And meanwhile, existing fuzzers cannot efficiently fuzz such a new file system. Yeah, there are lots of challenges to fuzz a file system. As we mentioned, there are two factors, image and file operations, that can be mutated for finding bugs. For example, for fuzzing an image is quite large in size for fuzzers, and fuzzers cannot handle such a big bulk of data. Moreover, for an image, only metadata matters. Mutating on user data like file contents is basically a waste of time because it cannot trigger any bugs at all. Talking about metadata, each file system has their own metadata structure design, often with a complicated hierarchy structure. So we have to develop a specific parser for extracting and maintaining this metadata. At last, there may be a checksum mechanism to ensure the integrity of all metadata. So after mutating on metadata, we have to fix these checksums or the amount will fail. Well, talking about fuzzing file operations, it is not an easy job because we have to generate syscalls for file operations, mutate arguments and of syscalls, which include lots of things like valid file descriptors, flags, and buffers. Also, the most important thing is that it should be context aware. For example, if we open a file, the following operations like fread, fwrite, and fclose should aware that this file is opened already. Okay, except for challenges we mentioned before, there is another dilemma. We know that fuzzing testing requires a runtime environment to dynamically run the target. So to test file systems, we can run operating systems in a real machine or a virtual machine. So there is a dilemma. Should we choose one of them? Their pros and cons are so obvious for fuzzing testing. To be specific, though testing on real machine can be really fast and the scalability issue can be solved by spending lots of money. However, it is too hard to be managed. I mean, it has to be rebooted every time, and the debug is also difficult for an operating system. Additionally, a virtual machine is not a wonderful option, and so its scalability can be easily solved by creating lots of instances, and its management is easy. However, it has a more slower speed, and it suffers aging OS issue. So we adopt new executor named libOS that is Linux kernel library, LKL. It can be basically seen as an application that can emulate behaviors of Linux kernel. So its execution speed depends on the device, and it is so easy to be rebooted or scale. Also, its bug is really easy to produce. The only disadvantages are it is not maintained anymore, so we have to manually upgrade it to the newest Linux kernel to make it compatible with the newest NTFS image. Also, some features are not supported, like memory management unit, SMP, and etc. So the solutions are clear, just upgrade it and introduce the features we need, that is CASM, that can detect the memory-related bugs during running the LKL. So the next thing, we have to choose a weapon for these fuzzing things. However, existing work all focus on either of the two factors like AFL and HomeFuzz can mutate a binary file that is an image, and syscaller and Trinity can mutate a program consists of series of operations. So do we have a fuzzer that takes all image and file operations into consideration? Fortunately, the answer is yes. Genus is a work published on SNP 19, and it is developed by Georgia Tech SS Lab. It is coverage-driven fuzzer that can take both image and file operations into consideration. And it also adopts LKL to emulate a runtime environment. However, it cannot directly be applied on the NTFS issue. First, it needs a specific image parser for NTFS because NTFS definitely has different metadata structure with other file systems. Also, maybe a more effective syscall fuzzer. Second, the library executor, I mean the LKL runtime environment is obsolete and not maintained anymore. Third, if we want to find some memory-related bugs, CASM is necessary. However, it is not integrated. So like what I said before, we have resolved the last two challenges by a bunch of engineering job on LKL. To resolve the first one, we have designed and implemented our own fuzzer, which is named Papora. Papora is a fuzzer specifically targets on NTFS file system. It consists of two core components. The first is image parser. As we can see, the image parser will first parse and extract all metadata from the given image and concatenate them as a piece of binary data. Then it will ask a mutator to play some common strategies like bit and byte flip on them. Then the image parser will map the metadata back to the original slots to the given image. Finally, the image will be sent to the LKL as a disk waiting for mounting. Of course, we will do some checksum fix up in this process. Also, Papora will play mutation on file operations. We will first generate a simple C program, and the syscall fuzzer will try to deserialize the program and extract all syscalls. The fuzzer has two operations: mutate arguments or functions of existing syscalls, or add another syscall after the original sequence. Whatever it takes, the program will be assembled and sent to the LKL as a program that will be executed after the image is mounted. Finally, the right table shows our results. And as we can see, we have identified 12 issues consisting of 9 bugs and 3 vulnerabilities, the highlighted rows. And all these 3 vulnerabilities are assigned CVE numbers. And moreover, we can see the last column, there were some marks, which means that these patches we committed to Linux kernel has been merged into the upstream. All these issues are divided into 2 categories. While the type 1 means that these bugs and vulnerabilities will be triggered once the image is mounted. However, the last type 2 related bugs will be triggered only after the syscall program is executed. We can see that most of these bugs are out-of-bound access, and 3 of them are about null pointer reference, and the others are about heap corruption. The root cause of these bugs are also interesting. Most of them are due to the lack of sandy check. Like a crafted offset could simply lead to an out-of-bound read if it is not bounded by the size of the allocated memory. So here are some takeaways. First of all, it is so obvious that because there is almost no hanging fruits right now. So for security researchers, such complicated and hard to find software is a good target. And file system maintainers should pay more attention on meta integrity check. That's what we found in type 1 issue. And users should be cautious on mounting a disk image. Our results show that malicious users can exploit your computer by just mounting a disk. And of course, we have open source both Papora and the upgraded LKL with caching integrated at this website in case if you are interested. The last thing, we have conducted several case studies under both types on how these issues are triggered and patched in our paper because we don't have enough time. So you can go check our paper on the UT website. So that's all. If you have any question, you can ask me directly. I will show up in the demo session or just send emails to either of these two addresses. Thank you, guys. So any questions?
Yes. Yeah. Do we have any questions for this talk? If not, I can maybe start. Okay. So you looked in this work at specifically NTFS fuzzing, but will you see that your approach of using the libOS-based approach also works for other file system parlors?
Yes. So you mean that I use the LKL? Yeah,
so more that whether your approach is portable to other file systems.
Yeah, of course. Our approach, you can say this. You can just write your own parser like JNS and its following work named Hydra. I think if you write your own image parser and do some checksum fix mechanism, it can be applied on other file systems.
Okay, great. Any other questions? Yes.
Good work. Great work. I was just curious. It seems as though the most impactful bugs, the security vulnerabilities, may not have been caught unless you adapted KASL. I'm sorry, KASAN.
KASAN.
Yeah. So for most of those, would those have been found without KASAN? Just curious.
I just think KASAN is a key component to find the heap corruption bugs. So I think it's necessary, and if we don't integrate KASAN, and we cannot find these two bugs. Yeah.